Hello YouTube viewers, welcome to my show Future Friday. In today's episode we're going to discuss a topic very important to space, deep space communication. So let's dive right into it. Well, first we have to understand this simple aspect. We need communication. You don't have to explain it. It's just basically an absolute need. It's like air. And there is a famous line: in space, no one can hear you scream. So even if, let's say, during Apollo 13, there was another capsule or another mission going on, they could not scream and like, bro, do this or do that. Like your side panel is blown off. You can't do that. And without communication, not only you can get stranded, it could become flat out fatal in certain scenarios. So it's not something like oh no, you have to have communication. Without communication, you dead. So what is the problem? Before we understand any topic, we must understand the physics behind it, because physics is let's put it this way, you cannot break it. So distance is huge. Now this aspect is very hard to psychologically understand, simply because we are humans. Basically, if you tell someone, hey, that's 100 kilometers away, they're like, okay, I can picture that, I can get that. You say 1000 kilometers, it's like, okay, they can understand it, visualize it to some extent. You say 6000, again, most people can't, because that is the diameter of Earth. Like, you are not familiar with the aspect, like, okay, Mount Everest from here is like 8000 kilometers. You're like, what? So you can understand, and that's on Earth. Like, we cannot facilitate triple digit or quadruple digit numbers with kilometers. And when you're talking about moon, that's 300,000 kilometers, more or less. It does changes depending on orbits and all that. So that is simply incomprehensible for human mind. Like, humans cannot comprehend that kind of number. So scientists, even they are also human, they also suffer from this. So they started to use light seconds. It's like how long light will take, which, mind you, is the fastest thing there is in this universe. It still takes 1 second. Basically, if you are communicating to the moon and you are sending data packets to there, it could take upwards of 1 whole second. So you can understand that, like, it's ludicrously far. And when you're talking about planets, it's like a whole different ballgame. People are like, okay, we went to the moon, why we can't go to Mars? I'm like, bro, moon is 1 light second. Mars, at best case scenario, is whole like multiple minutes. It's like 6 minutes, and that is the best case scenario when Earth and Mars are the closest. Sometimes when they are like Earth is here and Sun is here and then Mars is on the other side, you're talking about ludicrous distance, as in 14 light minutes. So you can understand that, like, a rocket that can go 1 light second versus a rocket that goes for like minutes, like light minutes, that's a completely different ballgame. So distance are huge. It's very hard to comprehend about that. Now, on top of that, let's say you've traveled there. Somehow you got there in 2 years or 6 months or whatever, or in case of Pluto, 10 years, you got there. Then there is another communication that issue that happens whenever you are sending radio waves or whatever. Like, almost every electromagnetic system suffers from this. It's known as Shannon Limit. Now, this is too complex for me to even understand, but think of this: this is a physical limitation. You cannot bypass this. Every signal has a noise to it, because everything creates noise. Planets, even planets, sun is like a very noisy thing. Whenever there is daylight and radio telescopes have to do analysis, they'll be like, okay, this whole area of sky, do not even point your radio telescope, you will fry it. You will just there will be a whole no aim zone. So if there is a lot of noisy sources on the universe, including Jupiter and Saturn and all that. Their radio signals are so intense, interference is so intense, you can catch it up in normal basically FM radio from cars and all that. So signal always has noise into it. Now that signal to noise ratio is our biggest enemy. If noise becomes high enough, does not matter how good your signal is, there is a limited number of data you can transmit with any integrity. Because even if, let's say, noise becomes too high, you can tell, okay, signal is there, but you can't discern it easily. What did you say? Like, all you will understand is like, okay, they said something, but what the heck did they say? You don't understand. Like, this is a physical limitation with like what kind of megahertz you are using, what is your signal to noise ratio, that will directly physically limit you. You cannot bypass this. That is like, okay, signal to noise ratio, that's like your bandwidth kind of hoo-ha. Then come to the power aspect, because again, light second, light minutes, you need power. Now power drop over distance, it's a very complicated thing known as inverse square law. I already made a video about that, you can find it in my channel. And to give you a rough idea of it, basically you start with 100 watt. Let's say you have a transmitter that is 100 watt. Now again, your mobile phone is like 1/10 watt. So let's say you transmit, you're like, okay, it's 100 watt, it should communicate for very distant. Here's the deal. By the time you reach, let's say 100 unit, like, let's say 1 unit, that's it. You're going 1 unit, you would have dropped it by basically 25. Another unit, you would have dropped it by 12.5. Another unit, you would have dropped it by 8 watts. You started with 100 and you have only 3 units apart. So you can understand, like, we lose power drastically. It's square, basically it's square cube, not cube, like it's inverted, right? Square root kind of scenario is happening here. So it's a very intensive. Basically you may have, like, 10 gigawatts of radio communication. By the time the signal reaches earth, it would be like, few microwatts. Like, you would need a radio telescope to communicate with it. So these are the physical problems. Like, first, it's ludicrously huge, far apart. On top of that, there is an inherent limitation. Like, if your signal is not clean enough, not signal to noise ratio is not high enough, even though you can receive it, you will not able to decipher it. On top of that, power drop off is like, that by default makes your signal slowly go into the noise of the background itself. So these are the physical problems. You cannot bypass this. So what are our current solutions? Well, when NASA as early as in like 1970, they started to realize they're gonna make multiple missions, like Viking missions, mission to Venus and all that. They need a way to communicate. Now here's the problem: all of these things are far apart. Like Mars could be anywhere, like in the sky, it could be anywhere. So they needed a way to cover the whole planet. Basically, they must be able to communicate from anywhere on the planet. So they come up with a simple network known as Deep Space Network. Very simple name, and they created 3 sites. Now these sites are Goldstone, California, Madrid, Spain, and Canterbury in Australia. These are the 3 sites. Now if you see Earth from a pole, you will find all these 3 sites are basically 120 degrees apart. So basically these 3 radio sites can cover 100% of the planet. Basically, no matter where you are in the solar system, you will receive a signal from these things. Anywhere, like in the plane of the solar system, you will receive signal from any of these. And when you see in the Martian movie that guy is aiming the dish to Earth, this is receiving the signal, not anything else. Like, these are the primary backbone of our space communication. Then you selected your site, you created a radio exclusion zone. So how the heck you receive the data here? Because I told you, like, power drop off is very dramatic. So we don't have normal telescopes and mobile towers of that nature. We have giant radio telescopes, and these telescopes are huge. I'm talking 70-meter diameter is the backbone. Like, that's huge. 70 meters is like a whole building is moving just to track your signal. So you can get that idea. Like, and all these 3 sites have that. And not only that, like, they also have another auxiliary antennas for additional data tracking or telemetry data. So that is how you actually receive the signal, and you make sure, like, you have always 100% coverage. And on top of that, because I specified noise is an inherent limitation, it's a physical limitation, you cannot bypass this. We generally cryogenically cool the damn receiver. Basically, receiver, no matter what its temperature is, let's say 20 degrees Celsius or 30 degrees, in Australia it would be definitely higher than that, but let's say that receiver is that temperature, the metal itself would be generating noise. Now that noise is not like, okay, radio noise is coming out of it, it's just noise is there, so signal is no longer clean. So we generally cool it down. We cool it as close to absolute zero as we can go. Again, metals have limit, you cannot cool a metal to absolute zero, it will shatter. So as low as we can take it, and we cool it out. That way our noise floor goes down. Once our noise floor is low enough, then we can receive even a very faint signal. So we have to do all this gibberish so we can receive signal from Voyager. To give you a context of Voyager is 1 light day apart. It's outside of our solar system. Even if you are traveling at light speed, it will still take you more than around 19 to 20 hours to reach it. It's almost a day apart. Like, that's ludicrously far. Sun from Earth is only 8 light minutes. So understand that, wrap that in your mind around it. How the heck we are communicating it? Basically this. So we are that was radio communication. Now we are moving to optical. Okay, why? Physics is simple. Higher the frequency, the higher the bandwidth. And I'm talking about bandwidth, I'm talking megabytes per second. Think of it this way: if you take a radio wave and you take, like, okay, 1 second pulse of it, you have 1 second. How many times it's going on and off? It's not enough. And the higher the frequency you go, the better you get. Simply think of it this way: you're a Wi-Fi router. It has two. Generally, it will have 2 bandwidths. It will have 2.5 gigahertz and it will have 5 gigahertz. 5 gigahertz are generally higher capacity because of the bandwidth. Like, it's going on off much more. So you are, even at the, like, it's on for only 1 second, you will be able to send much more high data. Now again, radio frequency, even at 5G high frequency, you are still talking about like 20-30 gigahertz. The moment you go to infrared, you are talking about 10,000 gigahertz. or you entering into 10 terahertz kind of ratio. So higher the frequency, higher the bandwidth. Okay, that solves one problem. Now you have a much bigger road of your communication. Then we utilize laser transmission. Why? Now again, laser also have its own variant of what we call inverse square law, but it's not as brutal as a radio system, because radio system is just, by the time you are reaching to the moon, it's like gibberish. So again, we can communicate it. I mean, like, we are doing it. It's just really, really bad. Like, to give you a context, they said like Voyager, I'm saying, the probe that went to Pluto, it took months to download the photo. Like, it took the photo, like took the photo, and it's like, yeah, transmitting here. I'll get you in, like, 2-3 months when we have the uncompressed file. Because first they always send the compressed data, so they will analyze the compressed. That itself could take weeks. So they will analyze the compressed data and like, okay, this photo is the best one. Then they will send the computer a signal, bro, send this file number and send it in uncompressed system. So that will take even longer. Sometimes they are saying like it could take upwards of years to download the whole system. So radio, you can understand that flat out the power drop is too high. Now this allows us to bypass it, not to complete extent. Do not think like, okay, you have laser communication, you can communicate to Alpha Centauri, because there is quantum uncertainty. The photons that are leaving, even if they are absolutely parallel, they won't be absolutely parallel forever. So they diverge over time. So if when we have a lot of experiment we do from Earth to Moon using lasers like that are pencil thick, they become like 100-kilometer wide once they reach the moon. And to give you a context of it, the maximum theoretical we can expect, it's around 1 light month. You cannot communicate, like, again, you can communicate, it will be just, you will receive noise and you will have like, okay, send Morse code rather than like, gigabytes of data, send Morse code. So we use laser is perfectly capable of doing high data transmission as far as Pluto or even as far as Voyager, because again, it will spread out, but it will be due to quantum uncertainty, but it will not be very severe as long as you are within 1 light month. So that's how we increase the range aspect. Then we have to utilize the telescope on the receiver, because I did say it does spread out. So you do not have to like, okay, I said the transmitter is like, let's say the laser beam that is coming out of it's 1 centimeter thick, I need 1 centimeter. No, you need a freaking telescope. And the NASA experiment that has been done, the telescope was like 1 meter to 3 meter range. So we need telescope, otherwise our sensitivity will go down and we will go back to square one. And the experiment, like the physical actual experiment, has been conducted and we successfully reached 600 Mbps. To give you a context, the Apollo era was barely kilobytes per second. So 600 Mbps, that is like 4K HD, like higher than that, you can do from moon to Earth. This has been done and I have provided the PDF down below. Please read it, like a lot of information is there, and this works. And the target is like, if you actually go to Mars, this will allow you very thorough, like a thick bandwidth connection. Now we come to the another hidden aspect of it. Whenever you are connecting to any server or any YouTube or any Facebook like that, there is a protocol that is handling all of these things. You're not supposed to worry about that. It's like, software engineers are dealing with that. Now problem is that space is big. I specified like it's measured in light seconds, light minutes, or light hours. It's big. On top of that, planets are far again, and not to mention their distance also changes. So that creates a physical reality known as lag becomes inevitable, almost like Thanos. So you cannot do anything about it. Like physics is flat out saying no, you have to deal with lag. So you cannot have a video conference. And I do like this aspect on the Elysium TV show. Elysium, I'm saying, the Expanse TV show. Like this is a whole core aspect. They have magic engines, they have magic juice and all that, but they never say like you are communicating faster than lag. They always have like communication delay 14 minutes, communication delay 30 minutes, and all that. So lag is inevitable. You cannot do anything around it. So problem is that our current communication, it's like this. So basically, let's say you have multiple links. You have your router, you have your satellites, you have your antennas and all that. And because everything is moving, they will not always be perfectly aligned. So what our current communication is like is basically it will wait. Okay, link 1 check, link 2 fail, it will stop the connection. It will let's say link 1 correct, link 2 correct, link 3 fail, it will still stop. Link 1 correct, link 2 correct, link 3 correct, link 4 fail, it will still not send the data. It will only send the data when everything is perfectly aligned. So it basically waits for you to create a pipe. Once the pipe is there, once the bit is going back and forth, so it confirms it like, okay, data has been received there, then it sends the data. And that is why your Wi-Fi is like so terrible the moment you start to increase the distance. It's not only it's increasing the lag, it's also waiting for it like, okay, did you receive the data, did you receive the data? And because of inverse square law, like few meters will like dropping your power too much. So NASA is creating a known system known as DTN. Again, it's a system, they are working around it, like a lot of details have to be worked out. But this DTN network will allow basically every node that you have, basically your satellite dish, your relay stations and all that, they will have a simply package holder. They will not wait like, okay, align everything and then we'll send the data. They will just like, okay, 1 to 2, okay, transfer from 1 to 2. Then like 2 to 3, transfer from 2 to 3. 2 to 4, transfer 2 to 4. So you get the idea. Like it is like more like a stop and go scenario. Benefit, bandwidth can be utilized, so you do not have to like, okay, satellite has to be perfectly aligned. It will never be like, satellite always have to keep moving, rotating and all that. So you will, signal drop will always be inevitable, and not to mention lag also physically will make it difficult. So but it can still transmit the data. It's just gonna be like every node in the system has to act as a buffer also. It's like, okay, we can absorb like, few gigabytes of data, then once we receive the new one, then we have to transmit this one once we get it on the line of sight. So it's a very different protocol, and it will change drastically the earth architecture also. Not only your satellite internet like Starlinks, OneWeb network and all that, it could also affect other things like optical networks and all that, because there are scenarios where even if you have optical, you have to deal with latency. So then we come to the final slide of the situation. Everything in physics always comes down to two core factors: efficiency and power. To give you a simpler idea of it, we generally measure the efficiency of a radio communication system is just by bits per watt. How much bit can you transmit using 1 watt? Basically, your mobile phones generally have like 5 or 6 watt of capacity in terms of battery, yet it can transmit like gigabytes of file over that. So it has very good what we call bytes per watt. Now when you are talking about satellites, not only they have severe limitation in terms of how much power they have, they also have a very inefficient system. Now you are like, why the heck NASA is using inefficient system? Well, think about this way: the mission that we sent to Pluto, that took 10 years. That means the radio communication on it is 10 years old by the time it was left. So now you're receiving signal from 10 years. So it's basically before 2G. So you can get that idea, like not before 2G, I think at 2G we have 2G equipment there. So that is one thing that every scientist and engineer is working their ass off to improve: bits per watt. On top of that, we have to reduce lost packet, because I told you like current internet protocol is like it throws away packets there is no tomorrow. It's like, oh, your signal failed, okay, resend the same packet. So we have to improve the protocols and all that, and NASA is working on it. Then we have to let's say you figured it out the best. Let's say you can transmit 1 terabyte per watt. Again, too much, but let's say you reached that kind of efficiency and you fix the package loss issue. On top of that, the final limitation would be the power. The larger the budget, the better the capacity you will have. Let's say in Lunar Gateway, they are like, okay, here's 100 watt that nobody will touch. This 100 watt is dedicated for your communication array. Good, we can communicate, everything is awesome. But let's say that's like, okay, now you have basically 1 kilowatt, let's say. That means every astronaut could have 4K live streaming. So that simple, it's very simple. Like, it's efficiency and power. Either you increase your power budget or you improve your efficiency, and in best case scenario, have your cake and eat it too. So this was my presentation on basically deep space communication. I hope you liked it, learn from it. In that case, please click the like button. If you didn't like it, didn't enjoy it, I'd urge you to press dislike, press twice to show me your disappointment, and please leave a comment because I reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.